Once you've mastered basic hypothesis testing, the next natural question comes to compare two populations together. Is one population bigger than the other? Does it have a higher average? Is the proportion smaller or different in one population versus another? To compare two populations, we do it just like we did with confidence intervals. So we look at the difference between them. We want to compare mean 1 versus mean 2. We'll compare or examine the difference. The null hypothesis is that the first mean equals the second mean. We just assume that the two populations are the same. Our alternative hypothesis can look then in any direction. Is the first mean greater than the second mean? Is the first mean less than the second mean? Or is the first mean simply different than the population or the mean of the second population? Therein we are looking at the differences. Another way to phrase this business about the differences is to structure them as differences. That would be that the null hypothesis is that the difference between the first and the second mean is 0. And alternative hypotheses that state the first mean minus the second mean. If the first mean is larger, the difference should be positive. Or the first mean minus the second mean. If the first mean is smaller, this difference will be negative. Or the first mean minus the second mean, is the difference simply not equal to 0? These are the same type of tests, one right-tailed, one left-tailed, and one two-tailed. It's simply a matter of how we structure the hypotheses. Now, there are 3 ways that we looked at to test hypothesis. 2 for means, 1 for proportions, and we're just going to modify those formulas to fit 2 different populations. When we know the population standard deviation, this is unlikely, but if they are known, then we are allowed to use the z-test statistic, z, created by x1 bar minus x2 bar, right? The difference between the two sample means divided by the square root of the first population standard deviation squared divided by the first sample size plus the second population standard deviation squared divided by the second sample size. If more likely, the population standard deviation is unknown, we cannot use a z-distribution, we must use a t-distribution, so we'll have a t-test statistic. Still, the numerator is the difference between the sample means, but we don't have population standard deviation, so we have to use the sample standard deviation as an estimator in its place. To find the degrees of freedom for the t-distribution here, we simply choose the smaller of n1 minus 1 or n2 minus 1. So from the smaller sample size, we just be the most conservative that we can be. Now, another option that is used by technology to calculate the degrees of freedom is using Satterthwaite's approximation. It's more accurate, but it's also much more complicated. The formula for that is available in your textbook, but when you run it on a calculator, this 2-sample t-test, you'll get a degrees of freedom that's from the Satterthwaite's approximation. You'll get the same test statistic, but a slightly different p-value on account of this approximation, which is larger and more accurate. When we are testing proportions, everything's with proportions is approximately normal, so in this case it's a z-distribution. Much like we covered when we simply tested proportions in one proportion, now we do 2, so p1 hat minus p2 hat, the difference between the sample proportions, divided by the square root of p bar times 1 minus p bar times 1 over n1 plus 1 over n2, where p bar, he's a new thing to you, is sort of this pooled measure of p, r1 plus r2 over n1 plus n2, or x1 plus x2 over n1 plus n2. And of course, p hat is x over n or r over n, depending on the notation you use. Either one, same trick, we're just making the proportion of the sample. Now, all these tests can be run in the calculator as well directly. If you just input the information that you're given. To run a proportion, you need the 2-sample proportion test. 2-sample proportion z-test. I don't think SAMP is there, so 2-prop z-test. To run it on a difference of means when we don't know the population standard deviation, that's a 2-sample t-test. When you get to the part that asks if the standard deviations are pooled, the answer is no. And when the population standard deviation is known, we can run this in the calculator by using the 2-sample z-test from the test menu. There's no shortage of words on these examples, so I like to read the problem one time, take inventory of what I have and what I know, and then move forward from that so I don't have to go back and weed through. So first, if you read this, you notice that we have 2 different shifts from Karen and Jody. Karen has a random sample of 35 shifts. Let's call that N1, first sample, size 35, with a mean from the sample X bar of population 1 of 5.2 calls per shift, and a population standard deviation that is given for both, and population standard deviation is sigma, is 1.3 for the first shift, and that's for Karen. Then we get some information for Jody. Jody had a sample of 34 shifts. The mean number of calls for the second sample, was 4.8, and the population standard deviation for the shift was 1.2. So once I take this inventory, that helps me. Now I don't have to read through again. We'll notice that population standard deviation was known and given. Therefore, we'll use a z-test. First step in doing the test is to determine the null and alternative hypotheses. When there are 2 populations involved, the null hypothesis is always that those 2 populations are the same. In the alternative hypothesis, we looked for the difference. Is it a left-tailed, right-tailed, or 2-tailed difference? In this case, we are just looking for 2-tailed. What's the probability that the first guy is different than the second? No, not probability, but likelihood. Is it statistically significant enough for us to claim that they are different? Step 2 is to actually calculate that z-test statistic. These are differences in means, x1 sample mean minus x2 sample mean, divided by the square root of population standard deviation 1 squared divided by sample size 1 plus population standard deviation 2 squared divided by sample size 2. That equals x1 bar is 5.2 minus x2 bar 4.8 divided by the square root of population standard deviation 1.3 squared divided by n1 is 35 plus population standard deviation 2 1.2 squared divided by sample size 2 34. Remember some good old parentheses in the numerator to make sure we find that difference and then make the division. The denominator can be very straightforward. Just type it in as he shows up. You'll get a z-score of 1.3286 or about 1.33. To find the p-value, of this. Remember, approximately normally distributed. The z-score is 1.33. We are looking at the probability of being larger than 1.33 or smaller than negative 1.33, and that's because it's two-tailed test. This thing is probably a common mistake when people get deep into the test statistic, find the p-value, move on with your life, and they forget to go back and look at the alternative hypothesis to see what tailed test it is. If it's two-tailed, we can find this probability from the table, but we want to multiply it by 2 because we could be on either direction for the probability here. Probability that z is greater than 1.33, so that's twice the value that we can find on the table at negative 1.33. That is 2 times 0.0918. If you have your table handy, you can check that out. It's 0.1836 once we multiply by 2 for a p-value. Fourth step is to make a decision. Is p less than alpha? If p is low, we will reject the null hypothesis. You see p is not low though. P is 0.1836. That's pretty good. That's not less than 0.05, which was the level of significance. So no, this is not the case. Therefore, we fail to reject the null hypothesis. The information from the sample is not statistically significant. It's not different enough from the assumption that the means are equal for us to support the alternative hypothesis that the mean number of calls per shift is truly different. To run this test in the calculator directly, get the test statistic right out of here, choose stat and tests, and then it's simply a matter of choosing the right test and putting the information in the right place. This is a 2-sample z-test, z because we have the population standard deviation given, and 2 samples because we're comparing 2. We'll input data from the 2 samples, but they kind of come in a weird order. The standard deviations first, then the means and the sample sizes of each. So just pay attention there. The standard deviation of the first population is 1.3. Second population is 1.2. The mean of the first sample, 5.2. Mean number of the first sample is 35. Mean of the second sample is 4.8. The size of the second sample is 34. And we are testing to see if the 2 are different. That's the first one. And calculate. You'll see this verifies the numbers we found by hand. The z-test statistic 1.3286 matches exactly. The p-value 0.18397, 1836. We are just a little bit off. That's just from a rounding error. Either one will be accepted into your homework. You can scroll down for more summary statistics. Just make sure that these match what you read from the problem. In case you get it wrong, you want to identify, perhaps you just typed in an error. This example is about filling bottles. Periodically, the company tests to see if there's a difference between the mean amounts of soda put in regular and in diet. So there's your 2 populations. A random sample of 14 bottles of regular is 14, with a mean of 501.6 milliliters and a standard deviation of 3.9. This standard deviation came from the sample, So it's not population standard deviation. Therefore, population standard deviation is unknown, and we will use a t-test. The second population is diet soda. The sample was 16 large. There's a mean of 498.9 and a standard deviation in the sample of 5.3 milliliters. We're testing a claim that the diet cola has a mean fill level less than that of regular cola, using a 0.01 level of significance. It's important to pay attention to the population selection in these problems. I noticed that there was a homework question that told you here, kind of like I did without explicitly saying it, regular was population 1 and diet is population 2. So the homework sets it up that way, but now you're testing that diet has a mean fill level less than regular. We told you that diet was the population number 2 and regular was population number 1. So directly translating the statement, we are trying to say that the mean fill level of the second population is less than the mean fill level of the first. If they're already selected for you here, which one's 1 and which one's 2, that affects our null and alternative hypothesis. The null hypothesis, not so much. It's just that the two means are equal to each other. The alternative, though, always compares the first to the second. So if we're testing here, the second is less than the first, that means that the first is more than the second in the alternative hypothesis. Not tricky, not complicated, just you have to understand what they're saying and be clear when you write it down. Second thing to do is calculate the test statistic. That's a t-test statistic. It's x1 bar, 501.6, minus x2 bar, 498.9, divided by the square root of the sample standard deviation 1, 3.9 squared, divided by sample size 1, 14, plus the sample standard deviation 2, 5.3 squared, divided by the second sample size, 16. Do this directly. Don't be shortcutting it and doing one little bit and rounding to some decimal places and then doing it again. You need to enter it all at one time to minimize any rounding error. I'll give you a preview of how that looks. On parenthesis, 501.6 minus 498.9 divided by the square root of 3.9 squared divided by 14 plus 5.3 squared divided by 16. And all that stuff under here is under the radical. No need for extra parentheses downstairs. Just keep them, multiply and exponents. The calculator knows the order of operations there, so just make sure that everything's under the radical and you're in good shape. That gives a test statistic of 1.602 to 3 decimal places. We talked about how to estimate the p-value of this test by reading across the degrees of freedom. In this case, to find the degrees of freedom, we need to find the smaller of the two options. N1 minus 1 is 13, that's the first sample size minus 1, and N2 minus 1 is 15. 16 minus 1, so 13 wins. 13 is our degrees of freedom. Our t-score was 1.602, so we'll open up, look across 13 rows, 13 degrees of freedom, find where 1.602 would belong in the table. Here's my t-table. 13 degrees of freedom. across here, the t-value I have is 1.602. So he'd be somewhere between 1.53 and 1.77. Go up here. Notice that we're talking about a one-tailed test, so we just need an alpha prime value. Means the p-value is between 0.075 and 0.05. We don't quite get to 0.05, right, because 1.77 is exactly 0.05, and we are not to 1.77, we're only 1.602, so our p-value is less than 0.075, but bigger than 0.05. 0.075 and 0.05. That's sufficient for us to make the conclusion, just so getting the range there is p less than alpha. Well, alpha was 0.01, and the p-value we got is bigger than 0.05 but less than 0.075. So even if we looked at this guy, which it's not even that small, it's not less than 0.01. So no, there's not sufficient evidence to support the alternative hypothesis, or we can say that we fail to reject the null hypothesis. There's not sufficient evidence from this claim, or from this test, to claim that there's a difference in fill levels, or that diet cola has been filled less than regular cola. To run this guy in the calculator, as soon as you identify that it's a t-test, notice also that it's a two-sample t-test. That's number 4. We have summary statistics, not raw data, so we'll put in those statistics. X bar 1 was 501.6. Standard deviation was 3.9 for that sample, and the sample size was 14. The mean of the second sample is 498.9. Standard deviation of the second sample is 5.3. And the second sample size is 16. The alternative hypothesis is that the first mean is greater than the second mean. And this is where it says pool. That's if they're going to pool the variances. If we have reason to believe the variances are the same, we can pool them. We don't have the reasons here, so we say no and ask it to calculate. You'll notice that a lot of our pieces match. Test statistics still 1.6, p-value 0.06. This is exact, fits on the range that we found. But the degrees of freedom are different. That 27.26, that comes from Satterthwaite's approximation. It's larger, it's more accurate. It helped us get this good p-value, but it's not going to affect our decision. 0.06 is not less than the level of significance of 0.05, or 0.01, excuse me. So either way, we would reject the null hypothesis, whether we look at the range or we find the exact p-value.